Welcome back. So let me remind you again. Let's start afresh and try to sell my propaganda. So there's this universal pattern, or at least a pattern that we see very often in nature. The Lefschetz theorem and Hodge-Riemann relations. So let's say you have your object X. Let's say it has a nice, sufficiently rich structure, whatever that means. So I'll keep everything sufficiently vague so that I cannot possibly be wrong. But at least I can say that your X may be a compact Kähler manifold of dimension D. So it is something like maybe a C to the D modulo discrete group lattice. That can be your X. That certainly counts as an object with sufficiently rich structure. Or maybe your X is a convex polytope of dimension D. This is simply the convex hull of a finite set of points in the affine space. And maybe it's a cube or the decahedron or any other particular polytope that you like. That certainly counts as an X with sufficiently rich structure. Or maybe you're an algebraic geometer and your X may be a projective variety of dimension D defined over some field. So solution set to a polynomial system of equations. Maybe it looks like that. That certainly counts as a sufficiently rich structure also. Or maybe you like highly symmetric objects, and your X may be a Coxeter group with an element of length D. So let's say a group given by generators and relations of the particular type, maybe that particular group, A square equal B square equal C square equal to AB to the cube, blah, 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 is equal to 1. Maybe it corresponds to some nice, very symmetric pictures like this or that. That, again, counts as a valid object X. Or you may be like me, and you like tropical geometry, whatever that is. So your X may be a tropical variety of dimension D. And that is a piecewise linear space, which is often, but not always, is obtained by tropicalizing algebraic or analytic objects, X, that you have seen on previous slides. So whatever the tropical variety is, they look like that. Piecewise linear objects. Sometimes constructed from algebraic varieties, some other times constructed from some other combinatorial or algebraic or analytic structures. That, I believe, should count as an object with sufficiently rich structure. So here is our list. And apparently, these are all objects with very, very different nature. Some are algebraic, some are geometric, some are combinatorial. They are all defined in different way. And although sometimes there are bridges connecting one world to the other world, but in general, there is this non-realizability issue. For example, your polytope may not be rational, and therefore there is no corresponding toric variety. And maybe your Coxeter group is not the Weil group of some crystallographic root system. And maybe your tropical variety is not a tropicalization of any algebraic variety, but just a tropical variety in its own right. Or maybe you have a geometric lattice or a matroid, as in the previous lecture, which is not realizable over any field. But still, sometimes it's known and other times it's conjectured that your object X should satisfy Poincare duality, Lefschetz theorem, and Hodge-Riemann relations. And as I have expressed in the previous lecture, I strongly believe that we can greatly expand this list. So, for example, I would expect there is and Hart-Lefschetz and Hodge-Riemann relations for objects like hyperbolic polynomials that you may meet in lectures tomorrow. But on this lecture, I'm going to concentrate on the Hodge-Riemann relations. And this is one quote that may be one of the early remarks that emphasize the importance of the Hodge-Riemann relations as opposed to Poincare duality or just Hart-Lefschetz theorem. So in a letter from Sayre to Grothendieck, it expresses, gives one statement that for some statement on zeta functions, or probably algebraic varieties, it says that it is sufficient to prove in all characteristics that the intersection form on primitive algebraic cycles of half dimension is definite. So that is the Hodge-Riemann relations. And in this particular context of A conjectures, it's supposed to imply something nice. So, but there are all these notion of primitivity and the corresponding definiteness for all the other objects that I have introduced in previous slides. So let me simplify the setup a little bit more. Not simplify, but give more structure to the general setup that I have introduced before. So I was talking about this Poincare duality pairing P and the Lefschetz operator L in quite a generality. But let's say my object X is sufficiently smooth, whatever that means. In such cases, you expect your graded vector space A that you associate to X to be not just any graded vector space, but in fact an algebra. There must be a multiplication within. So AX is the graded sum of AQX as before. This I'm just going to casually call it the cohomology ring of X. And in the smooth case, you can replace the structure coming from the Poincare pairing P by a single linear map that sometimes we call the degree map. It is a linear map going from the top degree component, A to the D in my notation, with values in the real numbers. And the Poincare duality pairing is induced by the structure of the multiplication and the existence of this degree map. And again, in all known cases, the Lefschetz operator L always comes in a family. It's not a single God-given operator. It usually comes in a family, and it varies inside an open convex cone. And every element in this open convex cone that I'm going to write by K have the same properties, the Hart-Lefschetz theorem property and the Hodge-Riemann relations. Of course, if you start with some completely random object X that you happen to like and try to build this structure AX with degree map and the Kähler cone KX, I mean, the real difficulty, I would say, is oftentimes not proving Poincare duality, Hart-Lefschetz, and Hodge-Riemann relations, but the real difficulty is formulating the three properties, namely defining or constructing the correct object AX from your X. This is often subtle, but fortunately, usually the very elementary invariance of X tells us or which direction to go when you are trying to construct the correct object AX. So once you have found the correct object AX to look at, then you would immediately conjecture that the standard conjectures to be true for any such X, your object X. This is maybe the whole point of constructing the correct object A. So in this format, the standard conjectures predicts that for any element L inside your cone K, living inside the degree 1 elements, so degree 1 graded piece, A1, and for every index Q at most D half, you should have, firstly, an isomorphism between A to the Q to the A to the D minus Q obtained by repeatedly multiplying L. So now my L is a degree 1 element in my algebra, so every time I multiply, I increase the degree by 1. And I should have a particular isomorphism between from A to the Q to A to the D minus Q. And the second is the Hodge-Riemann relation. So this is the subtle property, probably the deepest among the Poincare duality Hart-Lefschetz and Hodge-Riemann package, which predicts that the Poincare duality pairing and the Lefschetz isomorphism predicted by the Hart-Lefschetz are intertwined in a certain very particular way. So more precisely, it predicts that the bilinear form defined on Q's graded piece A to the Q, obtained by saying that the pair H1 and H2 is mapped to up to some sign, minus 1 to the Q, of the degree of L to the D minus 2Q times H1 times H2. Is positive definite. Not on the whole space, but when you restrict to the kernel of the multiplication by L to the D minus 2Q plus 1. So let me explain this exponents. So if you start from the Q's graded piece and start multiplying by L until you arrive at the complementary degree, the Hart-Lefschetz theorem predicts that this is an isomorphism. But if you go one step more by multiplying L one more time, then it will no longer be an isomorphism, and it will create a kernel. This is the space of primitive cycles that was referred to in the letter that I cited. And the statement of the Hodge-Riemann relations is that this bilinear form on Q's graded piece obtained by intertwining the Poincare duality pairing and the Lefschetz isomorphism is positive definite on the space of primitive cycles. So this is very different from Poincare duality and Hart-Lefschetz theorem. Poincare duality says something is non-degenerate. Hart-Lefschetz says that something is isomorphism. So in both cases, it essentially says that some number is non-zero. It's a non-degeneracy statement. Maybe a determinant is non-zero. But what is claimed in the Hodge-Riemann relations is essentially different. It says that some number or some collection of numbers are positive. So it's not just non-vanishing, it's a positivity statement. So most of the objects that I showed you on the first few slides are known or conjectured to satisfy Hart-Lefschetz theorem and the Hodge-Riemann relations in suitable setting. So let me just try to indicate that the proof was not actually trivial just by showing you a bunch of names and the important years involved in the proof. So Lefschetz proved the most classical case of compact Kähler manifolds in the 20s, and Hodge, using his theory, gave more correct proof. And then a few more years later, he gave even more correct proof. And again, a few years later, he gave even more correct proof. And Hermann Weyl gave a correct proof. So in the case of convex polytopes, there are several names involved along spanning decades. And it also has an interesting story. And Stanley famously used the Hart-Lefschetz part of this package to prove Peter McMullen's G conjecture, which gives a complete numerical characterization of all possible sequences f0, f1, fd for simplicial polytopes. So Fi is the number of I-dimensional faces of your given D-dimensional simplicial polytope. So Hart-Lefschetz property in this setting, although I have not really formulated it for you, at least it has a very important consequence. And Hodge-Riemann relations also holds in the case when your X is a convex polytope, and the very special case of the Hodge-Riemann relations, in the case Q equals 1, for all convex polytope, is known to be equivalent to what is called the Alexander-Fenchel inequality in convex analysis, one of the foundational inequalities in the theory of convex bodies and convex functions. For, say, smooth projective varieties, you can formulate an interesting one version of the Hart-Lefschetz and Hodge-Riemann relations and Poincare duality for a certain cohomology theory built out from algebraic subvarieties of your X. And this is Grothendieck standard conjectures from 60s. And it also is known to have important consequences like the Weil conjectures. And for the case when your X is Coxeter groups, this is the famous recent work of Ben Elias and Jordi Williamson. And again, you can formulate it for arbitrary Coxeter groups, whether it's Weil group or not. And furthermore, in this case, we can even prove it. And it again has important consequences like Rastenlustig positivity conjectures and other conjectures of Sorel-Gell. So apparently, these patterns both ubiquitous and fundamental in the sense that you see them everywhere, and whenever you see it, it has an important consequence. And concerning my favorite objects, tropical varieties, in full generality, we are not yet sure how to formulate the statements that are supposed to be proved. But I'm sure there are many, many more Hart-Lefschetz theorems out there waiting to be discovered. So let me show you one very simple case of the Hodge-Riemann relations. Maybe the simplest case concerning all the X's that you have seen before. So my X basically is a generalization of a graph. And as you know, very few things can be simpler than graphs in mathematics. So just two components, vertices and edges, and you just tell them which vertices are connected to which. And this is a manifestation of the Hodge-Riemann relation. It's a certain very universal statement concerning graphs. And the story starts from Hassel-Whitney, who, following his teacher Barkov, defined the chromatic polynomial of any finite graph G. So it is defined initially as a function with the domain, the natural numbers, and target also. And the value of this function associated to a graph G at a particular natural number Q is the number of ways to color the vertices of your graph using Q colors, with one condition that you have to use two different colors when the two vertices are connected by an edge. That's a function. For example, if your graph is this graph with 4 vertices and 5 edges, it turns out that your function is in fact a polynomial in Q. So if you want to know in how many different ways you can color your graph using 2 colors, all you have to do is plug in Q equals 2 to your polynomial, which happens to be a root of your polynomial. So the answer is 0, and you can immediately see why you cannot color your graph using 2 colors. Your graph is not bipartite. But you can plug in Q equals 3 to figure out that there are exactly 6 different ways to color the vertices of your graph using 3 different colors and so on. So, of course, you can ask many subtle things about these chromatic polynomials of graphs for a particular class of graphs. But what I'm interested in is what can be possibly true for chromatic polynomials for all graphs. So it's something very universal. And the expectation was that whenever you write down this function, which happens to be a polynomial, and read off its coefficients, say a0, a1, a2, dot, 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 then you should always see this convexity inequality. ai square should be at least ai minus 1 times ai plus 1 for every index I. So in the example you're seeing above, 5 square is larger than 1 times 8, and 8 square is larger than 5 times 4. And it is such a universal prediction. It's supposed to be true for all finite graphs, not just particular subtle class of graphs like planar graphs or anything. But so how can it be true without having a trivial proof? So let me try to again convince you that this is not actually trivial to prove, say by the obvious induction. So I would bet that if I give you 30 seconds, this is what you would do by induction. So you start with your graph, and you construct 2 new graphs by picking up an edge. Let's say I pick up the diagonal edge, and the first graph I'm going to construct is obtained by deleting the chosen edge, and the second graph that I'm going to construct will be obtained by contracting the chosen edge. So you see 3 graphs now, and you observe that the number of ways to color the vertices of the original graph, chi gq, using q colors, is the difference of the same functions using q colors of the 2 graphs that you have introduced. So there's less restriction for the deleted graph, and those exactly corresponds to the number of ways to color the contracted graphs. So that's the obvious recursive description of the chromatic polynomial, which happens to show that why the chromatic polynomials are indeed polynomials. This is a proof of the fact that chromatic function is actually a polynomial by induction, because the trivial cases are polynomials. But what it does not show you is that this algorithmic description of the chromatic polynomial makes it quite far from trivial. Why the previous prediction must be true, because this quadratic inequality that you have seen before, the log concavity inequality, is not preserved under the sum of 2 sequences. In general, if you add up 2 sequences, each one of them satisfying this quadratic inequality, the sum will fail to satisfy this quadratic inequality, unless you are always multiplying in some very particular sequences in particular way. So let me show you the same, essentially the same manifestation of the Hodge-Riemann relations, again in elementary terms. So as in the previous lecture, let's start with the collection of vectors in a vector space over some field. Let's say I pick up my same old 7 points over a field with 2 elements inside projective plane, so that I see that picture. And then I'm going to count, this time, not the number of points and lines, but rather the number of independent subsets of my vector configuration with given cardinality. So each subspace will be counted with some multiplicity. So in this case, where I pick all 7 non-zero vectors in 3-dimensional space over F2, the numbers will be 1, corresponding to the empty subset, which is independent, and 7, corresponding to 7 independent subsets of cardinality 1, and 21, which is 7 choose 2, and 28, which is 7 choose 3, minus 7, because you see 7 lines in the picture of the projective plane, which exactly corresponds to the number of triples that are dependent. So again, you see the Hodge-Riemann relations. And what is it in this case? Maybe I missed one remark. let me just, without going into details, let me convince you that this is essentially the same type of invariance in the case of chromatic polynomials. So if I give you the configuration, how would you compute these sequence fi? I bet this is what you would do. You start from your configuration, cook up two new configurations by picking up a vector, say non-zero. The first configuration that you are going to create is obtained by deleting the chosen vector, and the second configuration that you are going to create will be obtained by projecting away from the vector. And you observe that the sequence fi is related by that additive recursive relation. But that makes this particular instance of the Hodge-Riemann relations rather non-trivial, because you expect for any such finite collection of vectors A in any vector space over any field, you should have fi square at least fi minus 1 times fi plus 1, which is a non-linear inequality, which is not preserved under arbitrary sum of two sequences. So there must be some extra structure that we should be able to capture from a given collection of vectors, which is not captured by this inclusion-exclusion type relation. And that is the Hodge-Riemann relation. So what is the object X that we are looking at here, really? The relevant object X here is a combinatorial structure called matroids, which I called geometric lattices in the previous lecture. And this combinatorial structure matroids, which is an old subject, is from a modern point of view, is a very special class of tropical varieties. There is a way of looking at these structures as a tropical linear spaces. This is the most basic instance of what is now called a tropical geometry. So let me show you what kind of structure that we are dealing with. So again, this is a finite structure. So let's say you have a finite set E. So this is the same E as I used in my lecture before. And the matroid M on E is a collection of subsets of E that I'm going to call flats. This corresponds to subspaces or spans of vectors in the case when E is coming from a vector configuration. But in general, you ask that this distinguished collection of subsets of my finite set E to satisfy axioms 1 and 2. The first simply says that your collection is closed under intersection. And the second says that if F is a flat, one of the distinguished subsets, then any element not in F is in exactly one flat covering F. So this is a subtle property. So the only, the structure really comes from the expression covering. So if you look at all your collection of flats as a poset, then there are relations which expresses that one element is immediately above or below some other flat. That is the cover relation. And the second axiom requires that if you have a flat, then any element not in F is in exactly one flat covering F. I hope you can see this from the geometric case, where flat literally corresponds to flats or subspaces. If you have a subspace, say in a projective space, spanned by certain sub-configuration of your points, then any point not in that subspace is partitioned by subspaces of dimension exactly one higher than the chosen subspace, according to which such covering flat that is contained in. So this is one easy or cheap way to construct such abstract configurations, namely to start with actual configurations. What you do is you start with a field K, any field K, and you construct a projective space, P to the D over K. That we know how to do. And we choose any finite subset, E, inside P to the D. And using this embedding, you declare a subset of E to be a flat if it is an intersection of E with a linear subspace of P to the D. And then you check that the two axioms that we have required are actually satisfied. And such matroids are said to be realizable over K, where your K is your field. So these are the pictures. So you have met the Fano matroid. It is an abstract combinatorial system that comes from the 7 points in P2 over F2. And that matroid, as an abstract collection, turns out to be realizable over K, where K is your field, if and only if your field has characteristic 2. If you delete that circular line, then you get another matroid, and that matroid is realizable over K if and only if characteristic of your K is not equal to 2. So both cases can happen. And there are some examples like this, case of non-Pappus configuration, of hypothetical 9-point configuration in some P2 that is not realizable over any field. In fact, that particular configuration is realizable in some sense, meaning that it can be constructed from P2 over a division ring. So some matroids are realizable over some field, others are not. So how many matroids are realizable over a field? So it turns out that almost all matroids are not realizable over any field. So this is really a new territory, and a very small portion of it is covered by algebraic geometry. For example, my use of decomposition theorem and the intersection cohomology Hodge-Riemann in the previous lecture does not apply to 100% of matroids. And this question of realizability is known to be connected to many other interesting problems. For example, when your K is Q, this problem is essentially the Hilbert-Tensor problem over Q. And for geometric fields like real numbers or complex numbers, there are universality theorems on what is called the realization spaces and so on. So in short, the question of realizability can be interesting and delicate. And most of the matroids are not realizable. But still, we do expect, and in fact, in some sense, we can prove Hodge-Lefschetz and Hodge-Riemann for all matroids. That is in agreement with the following more general conjecture. So there is a certain numerical invariant, again a polynomial in one variable Q, which generalizes the chromatic polynomial in the case of graphs, and this independent set counting polynomial F in the case of vector configurations. It can be defined using the same additive recursion by deleting and contracting. And the same numerical, the quadratic inequalities, was believed to be true. Mu I squared is at least mu I minus 1 times mu I plus 1. And this is indeed more general than the conjecture on the graph and the conjecture on the vector configuration, because you can construct a matroid out of a graph and a matroid out of a vector configuration. And this conjecture specializes to the two previous special cases. So I guess there is a little point in going into details, but let me again once more emphasize that from a modern point of view, these matroids are special cases of tropical varieties, more specifically tropical linear space. So you can view a matroid as an abstract collection of subsets of a given finite set, like that, corresponding to 4 general vectors in plane, or as a certain piecewise linear geometrical object, like that. That's the picture of the tropical plane inside 3 space. So that is actually a picture of a fan, a collection of cones meeting each other in a very nice way, like simplicial complexes do. And the standard construction in algebraic geometry more precisely toric geometry, associate a toric variety, a certain algebraic variety with a large group action corresponding to any such picture and with the choice of any field. So if I pick my complex numbers and apply this construction to that particular picture, the picture of a fan, then what I get is the projective space CP3 minus 4 points. So I have to delete away 4 points because I don't have those 4 vacuum, I don't have, so that 4 big regions are empty in my picture of my fan. But you can do this to any fan, and in particular to the tropical linear spaces constructed out of a matroid. So if M is a matroid on the ground set E of cardinality n plus 1, then you can construct this fan, let's say sigma M, and from this, and together with choice of any field, whether your M is realizable over that field or not, you can always construct this toric variety X of a sigma M, say over the complex numbers. And this will going to be, in general, a non-compact, in fact, smooth complex manifold of dimension n, where n is coming from the cardinality of your finite set. But the first observation toward the Hodge-Lefschetz and the Hodge-Riemann relation is that something interesting happens when your matroid is realizable over some particular field K. And in fact, only it happens. It happens that there is a Chow equivalence from a smooth and projective variety over K, where K is your any field, to this non-compact toric variety X constructed out of my matroid, if and only if my matroid M is realizable over that field K. And here, Chow equivalence means the following. There is a map from a smooth projective variety over K, so let's say V, to the X, which induces, by pullback, an isomorphism between the cohomology rings, the algebraic cohomology rings, by which I mean the ring of algebraic cycles or subvarieties modulo homological equivalence. So what does it say? Let's say I pick my favorite matroid M, which happens to be realizable over the complex numbers. I construct this n-dimensional non-compact complex manifold. The theorem tells me that my non-compact toric variety of dimension n is in fact at the level of Chow rings or algebraic cycles is the same as a smooth projective variety of necessarily smaller dimension. And therefore, it should satisfy all those nice properties that are supposed to be true for all smooth projective varieties. So it is tempting to think this as some version of a homotopy or a retraction at the level of Chow theory. But the interesting fact is that even when the base field is complex numbers, this is not actually the usual homotopy. And this is, you see already from the case of the CP3 minus 4 points. So if you look at CP3, remove away 4 points. It is a non-compact complex manifold, and its singular cohomology is something horrible. It doesn't have Poincare duality or anything. But if you just look at the Chow ring, or the ring of algebraic cycles modulo numerical equivalence, it is something nice. It satisfies Poincare duality of smaller dimension, and in fact, Hodge-Lefschetz property of smaller dimension and the Hodge-Riemann relation for smaller dimension. In fact, it is Chow equivalent to a general P2 inside that P3 not meeting those 4 deleted points. The inclusion of a general plane is a Chow equivalence. So using the one direction of this observation, you immediately see that the Chow ring of this non-compact manifold satisfy Hodge-Lefschetz and Hodge-Riemann of different dimension than it's expected. But what can be shown is that even in the non-realizable case, if you just look at the algebraic cycles in this non-compact toric variety, it does satisfy Poincare duality, Hart-Lefschetz, and Hodge-Riemann relations of some smaller dimension. And that smaller dimension is again given by a combinatorial invariant of the matroid. And the statement has nothing to do with the choice of a field. So what you can do from any tropical variety, a certain piecewise linear object living inside Rn, say, you can think of a ring of piecewise polynomial functions, modulo global linear functions. It's a sum ring defined from both geometric properties of the embedding and the combinatorial properties of my piecewise linear object. And this ring is equipped with the degree map that we have discussed in the very first slide. And not only that, it is equipped with a certain canonical notion of ampleness, or convexity more precisely. We can talk about when a PL function on my tropical variety is strictly convex or not. When it is strictly convex, I declare its class to be ample. But in the case of matroids, I don't even have to go that far in the tropical geometry. You don't really have to read it, but I have put there just to convince you that in the case of matroids, every object that's involved in the statement are completely explicit and absolutely elementary. So my ring, the cohomology ring associated to any matroid M, will be a quotient of polynomial ring where variables are labeled by flats, and there are two types of defining relations. One, quadratic monomials, and the other, linear relations, just like the Chow ring of M0 M bar. And here's the second bit of information that we need, the degree map. So just like complex manifolds and projective varieties, it is important to notice that these rings, A of tropical varieties, are not just rings, but it is equipped with a canonical choice of orientation so that we can speak about when a top degree element is positive, 0, or negative. So this is crucial when we are trying to formulate something like Hodge-Riemann relations. We don't need this in the case of Hart-Lefschetz. We just need the notion of non-zeroness. It's already there. But for the Hodge-Riemann, we want to say when an element is positive or negative. And tropical varieties are equipped with that notion. So in the case of matroids, there's a completely explicit way of defining an orientation. And there's always a preferred one. And again, there's a God-given notion of the Kählerness in this abstract combinatorial setting. Of course, it will going to be the collection of all strictly convex PL functions on my tropical variety. But since I have not told you what my tropical variety looks like, I can translate easily back to the elementary language at the set theory level. So I'm going to declare a function on the Boolean lattice with values in the real numbers to be strictly convex or strictly submodular if those two conditions are verified. Its value on the empty set is 0, on the entire set is 0, and in every other case where you have pair of incomparable subsets in my finite set I1 and I2, you should have that convexity. That I declare to be ample or convex. And whenever you are given such a strictly submodular function, you can use it to define a degree 1 element in my cohomology ring A1. So remember, you can think of A as an explicitly given commutative ring by generators and relations, or you can think of it as the Chow ring of the non-compact toric variety I have shown you by picture, or you can think of it as the ring of piecewise polynomial functions, modular global linear functions, in this tropical variety corresponding to a matroid. But in any case, such a ring is equipped with the notion of positivity in two different ways. by the existence of the God-given degree map and the God-given Kähler-ness in degree 1. And this is what we proved with Karima Di Prasito and Eric Katz. And the statements are what you would expect. So you have all the ingredients that you need to at least formulate the three properties: Poincare duality, Hart-Lefschetz property, and the Hodge-Riemann relations. And the result is simply that those three properties are true. So I'll omit the Poincare duality part and start with the Hart-Lefschetz. You start with any strictly submodular function in the sense that I've described before. And there will be a corresponding degree 1 element. And the first part says that repeated multiplication by that element induces an isomorphism from a to the q to the a to the all minus q. So that all should be d to be consistent with before. And the second, the more subtle statement, is the Hodge-Riemann relation. It says that this symmetric bilinear form, the Hodge-Riemann form on q-graded piece, for every q at most d half, is positive definite on its primitive subspace, the kernel of the multiplication by L to the d minus 2q plus 1. And this time, it is the second statement that is responsible for all these quadratic inequalities. So in particular, this Hodge-Riemann relation implies the same conjecture for that matroid, the quadratic inequality conjecture, low concavity conjecture for that matroid. So let me try to convince you why that is the case. So actually, to deduce the conclusions of those low concavity conjectures, you only need very small part of the Hodge-Riemann relations, the case when your q equals 1. So A1 times A1 going to the real numbers. In any case, the Hodge-Riemann relations basically says that bunch of minors of certain matrices constructed from the structure of the multiplication has positive minors. And the relation to the low concavity inequality, which says that when you have triple A, B, C, then the middle one squared, B squared, is larger than A times C, corresponds to the statement that the symmetric 2 by 2 matrix A, B, B, C has non-positive determinant. And that is, in fact, the very special case of the Hodge-Riemann relations you get by restricting your Hodge-Riemann form to a carefully chosen subspaces. And it directly corresponds to the case of the convex analysis, the Alexander-Fenchel inequality, which says that a sequence of mixed volumes for any two given polytopes should satisfy that determinantal inequality. So unfortunately, although this general version of the Hart-Lefschetz and the Hodge-Riemann, which are valid for arbitrary matroids, are very closely related to the application that I have described in the first lecture, this is not sufficient to deduce the top-heavy conjecture that we talked about in the first lecture. So what is missing is that, so this basically describes, in the geometry case, the cohomology of the resolution that I have described. There is this thing below the image, which is very singular, and this structure of the morphism comes into the decomposition theorem and the intersection cohomology of the singular guy downstairs. That's completely missing in this picture. So let me show you why it may be a little bit easier to prove these statements in smooth case. So what we do to prove these statements is the following. If you give me two matroids, I view them as tropical varieties. Both of them are smooth in suitable sense. And let's say they are defined on the same ground set and they have the same rank. So they have roughly the same size and dimension. And what we show is that we can transform one tropical variety to the other tropical variety by repeatedly applying this local modification that we call flips. We don't change the whole thing at once. we change little by little locally. But I start at one tropical variety of interest and arrive at the other variety. And we can show that each one of the intermediate tropical varieties all have very nice cohomology rings satisfying hard Lefschetz and Hodge-Riemann by working at a flip, one at a time. But because any two matroids, tropical varieties, can be connected to each other by this sequence of flips, if you know the hard Lefschetz for any one particularly chosen matroid, if the hard Lefschetz and Hodge-Riemann is true for that case, then every matroid should satisfy a hard Lefschetz and Hodge-Riemann. So the argument is very much similar to the case of the weak factorization theorem for birational maps in algebraic geometry. You have one smooth thing, some other smooth thing. You can go from one to the other if they are, so long as they are birational. And you basically have to analyze one blow-up at a time to see what happens. But I believe that the picture extends much more than this. And in particular, I believe the language of tropical geometry can be pushed to give a framework to at least prove the top-heavy conjecture in the first lecture for arbitrary matroids, possibly not realizable over any field, or even the case of arbitrary tropical varieties and the maps between them. So what is missing is the good notion of tropical varieties and the maps, the kind of maps that should be allowed between them. Then one should have a nice notion of cohomology rings associated to such maps. And there will going to be a pullback map between these cohomology rings. And what you want to look for is the statement of the decomposition theorem and the general hard Lefschetz statement in what would be the tropically singular case. So I'm going to stop here. Thank you.
Questions?
Talk about Hodge-Riemann over the reals, but that's kind of discouraging for people who are going to practice P. Do you have any suggestion that anything that might use in its place?
Well, to me, working over characteristic P means that my object X is defined over characteristic P, and not that my graded algebra A is defined over characteristic P. So in short, I don't have the good answer to your question, but to justify my point of view, when your X, whether it's defined over characteristic P or possibly not even over any field, if you're expecting something very nice from it, your graded algebra A will be defined over real numbers, or in good cases, even over Q. I would like to think of this A as the collection of algebraic cycles in that sense. So maybe your étale cohomology is not defined over Q, but that's fine. I have a sub-object that's coming from cycles, algebraic cycles, and the sub-object can be defined over Q. And their positivity makes sense, and I can ask about Hodge-Riemann relations.
More questions? In your flips, which M prime do you use?
Huh?
So these flips preserve the validity of the statement.
That's right.
Then finally you have to check it for.
That's right. I can basically check it for the Boolean case again.